So now that we all know how to build series, right, power series, and we started using them by uh, building series of other functions and then using them to integrate. I believe I did the one example for you. The first problem in this packet wants us to, again, basically prove to ourselves that these approximations are a good idea. So they give us that the sine of x is equal to a summation from 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And they ask us to prove, or to approximate, sine of the square root of 5. So it says, first use the first three terms. So the first term, we're going to plug in 0 for all the n's. So -1 to the 0, x to the 2 times 0 plus 1, over 2 times 0, plus 1 factorial. That smudge looks pretty blurry. That better? So that's the first term, and then the second term, -1 to the first, x to the 2 times 1 plus 1, over 2 times 1 plus 1 factorial, and the third term, looks like that. So rewriting those, that's going to be x that we get out of this. -1 to the 0 is 1. 1 factorial is 1. And this is x to the 1. So we get x out of that one. And then we get, for this one, we're going to get a negative x cubed over 3 factorial. And the next one's going to become plus, because that's a -1 squared. And that's x to the 5th over 5 factorial. So those are the first three terms of the sine. If we wanted to keep going, then we could go all the way up to the 10 terms that they asked for. So let me just go ahead and write those out while we're here. Again, once you figure out the pattern, not that hard, right? Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and finally 10. So that's all 10 terms. Part A says use these three. Part B says use the first 6. And then part C is use all of them. So part A, if you plug in square root of 5 for x into these three terms, you will get 0.838525 to 5 decimal places. If you use the first 6 terms plugging in square root of 5, you get 0.786744. And if you use all 10, you get 0.786749. The actual value given by the calculator is 0.786749, at least to 5 decimal places. And the last part just says compare and comment on the error. So just use a percent error, which would be to take the value that you have, subtract it from this value, divide by this value, and multiply by 100. So for instance, if we wanted to do B, right, that would be 0.7866749 minus 0.786744 all over 0.786749 times 100%. So any questions about that problem? Again, that's kind of a review thing to just kind of say, hey, look, this is relevant. So everybody's good with that one? Okay. So I'd already done the first integration example for you, correct? Real quick, what did you plug in for x? Oh, the problem was square root of 5, so square root of 5 everywhere. So I did do this one already for you, right? The integral from 0 to 0.4, 1 over 1 plus x to the 4th dx. Parthy, is that just because of your special notes, or that I did do that one last time? Okay, good. So I'm assuming if you guys didn't recall or wanted me to go over it again, you would have said something just then. So I'm going to go ahead and continue. So we have another example here just like it. And it says, please evaluate this integral. 0 to 1 cosine of x dx. Now this is one that we could very easily do by hand, but why not do it with this method to prove that it's valid? So again, it says use the first 6 terms given that cosine of x is equal to the sum from 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. So let's write out the first 6 terms. So the first term is when n is 0. Negative 1 to the 0 is positive 1. X to the 0 is 1. 0 factorial is 1. So first term is 1. Then the next term is when n equals 1. So it's going to make it negative. That's going to become x squared and 2 factorial. Wait, I see. I didn't notice the problem has square root of x in here. Sorry about that. Okay, square root of x. So that's cosine x. So what would the cosine of the square root of x look like? So I would replace x with square root of x and do the same thing to that x. Everybody okay with that step? Okay. So if I simplify this, x to the 1/2, then to the 2n, that 2 and that 1/2 cancel. And so I'm just left with x to the n here. Okay, so now when I'm building my first 6 terms, I'm not using this one any longer. I'm using that one over there. Because I'm trying to find cosine of the square root of x. So my first term is still 1. Plugging in 2, I still get negative, or sorry, plugging in n equal 1, I still get a negative. Then I get x to the first power and over 2 factorial. Then if I plug in n equal 2, I get plus, because it's negative 1 squared, x to the second power, and I get divided by 4 factorial. So let me just write out the rest of the terms here. See, I got 1, 2, 3, 4, 5, 6. So that's the first 6 terms. And if I want to approximate this function, which I just wrote out the first 6 terms of, well, then I just need to integrate these terms. And again, a little word of caution. One thing I notice students do quite often is, for some reason, they'll get these terms and they'll forget to integrate. They'll just plug the numbers in. So we got to integrate this first. So this is going to be x minus x squared over, now there's already a 2 factorial down there, so it's going to be 2 times 2 factorial. This one's going to be x cubed over 3 times 4 factorial. X to the 4th over 4 times 6 factorial, and so on. all evaluated from 0 to 1. Again, the nice thing about plugging in 0 here is everything goes to 0, so really only got to worry about plugging in 1. So let's see, this is 1 plus, or sorry, 1 minus. It's going to be 1 over 2 times 2 factorial, that's 4, plus 1 over 3 times 4 factorial. That is, what's 72, I think. Check myself there. I figure out what I do with the calculator. There we go. So 4 factorial times 3. Oops. Yeah, 72. Minus 1 over 4 times 6 factorial is 2,880 plus 1 over 5 times 8 factorial. Now we're getting into thousands. And that one's divided by 21 million. So finally, let's put that all together. Okay, I get 0.7635465,811. That's my approximation. So then the question is, what is the actual answer? So we can do the FNINT function from 0 to 1, cosine of the square root of x with respect to x, and that comes out as that. So that is good all the way out to that digit. So 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places accuracy. Not bad. Not bad at all. And again, you might be sitting there going, yeah, but that's, it's a decent amount of work and got to figure out a lot of stuff, but how else do you integrate that? Right? We don't have a U substitution. Maybe by parts would be a possibility. Pretty much all the techniques of integration that we've used so far, other than to maybe look it up in a table somewhere, wouldn't help us very much. So any questions about that guy? So I guess I'm going to assume that you guys are good. All right. So I think we have one more task left in this packet, and we will be done the material for the next exam. So if you all have some questions, I'll be glad to answer them. All right. The last part here is another calculus application, but not integration. So this first one here is limit x approaches 0, sine x minus x over x cubed. Can you guys see that okay, the green? All right. So if I try to go ahead and do direct substitution here, sine of 0 is 0. That would be 0 as well, and so would that. So we get 0 over 0. So an option here is L'Hopital's rule. But instead, we'd like to go ahead and try to do an approximation. So again, power series are polynomial functions, which means I'm going to leave the x and the x cubed alone. I am going to replace the sine of x. So, does anybody have the power series sheet that I gave to you on Blackboard? If so, can you tell me maybe the first 4 terms of sine of x? So the first term should be x, right? Then what about after that? So I see we've got x cubed over 3 factorial. X to the 5th over 5 factorial. And it would be 7 over 7 factorial, right? Okay. So I'm just going to take the first 4. I'm going to replace sine of x in my limit there by these 4 polynomials. Or this polynomial, I should say. So limit x approaches 0. I'm replacing sine with all of these. Then I have minus x all over x cubed. So my x's would cancel. And then I'm going to divide every one of these terms by x cubed. Everybody agree with those? Maybe bring this just a little bit closer. See if it'll focus better. Seems like it brightens up when I come into the picture. It's kind of strange. That's what I put. You guys can see that? Alright, fantastic. So, if I let x go to 0 now, what happens? The two terms here that have x's in them will be 0, and I'll be left with just this, which is minus 1/6. So my next question is, how did I know that I didn't need more than 4 terms? So the way that I know that is I noticed that when I plugged in, I was going to divide everything by x cubed. And so any term that has more than just x cubed up top is going to end up going to 0 because it'll have some x left in the numerator. So in fact, I really didn't need to take any more than the first 2. But I took a few more just to demonstrate it. So let's try the last one. Okay, so the last problem here says, tell us the limit as x approaches 0 of x squared e to the x over cosine x minus 1. And if you plug in 0 right off the bat, then you would get 0 times 1 over 1 minus 1, or 0 over 0. Again, indicating L'Hopital's rule is applicable. But because we're doing this section, let's try plugging in for something. So x squared is something we should keep. It is already a polynomial. And we can even keep the minus 1 down here. So we need to replace the e to the x and the cosine x, right? Anything basically that's not a polynomial function. So, e to the x. How many terms will I need? Well, let's start writing out e to the x. So e to the x is some x to the n over n factorial, right? So the first term is going to be 1, then plus x squared over 2, x cubed over 6, and so on, right? And then cosine x, we just did 2 problems ago. That's 1 minus x squared over 2 plus x to the 4th over, what is that, 24, and so on. So again, I'm assuming that I don't need to take a ton of terms. On the top, because there's an x squared term here, if they were divided by x squared, that'd be a good idea to get rid of. And on the bottom, we've got a minus 1. So I know that if I only take one term, I get 0. So that's not good. So I need at least 2 terms. Let's go ahead and take, I guess, the first 3 here and the first 3 here and see what happens. So I have the limit x approaches 0 of x squared. E to the x is going to be replaced by 1 plus x squared over 2. And on the bottom, I have 1 minus x squared over 2 plus x to the 4th over 24, all minus 1. So I know that your instinct is to go ahead and trudge through multiplying that x squared in there, but I'm going to leave it outside for a second. Because down here I have 1 minus 1, they cancel. So then I have this. And one thing I noticed there is that all of those terms in the denominator have an x squared in them. So I'm going to factor it out. Still on the screen. Okay. So then I can get rid of these. And the reason I wanted to do that was because, again, I'm letting x go to 0. So any term that has an x in it goes to 0. So if I look at this right here, well, I get 0 times something, right? That's going to give me 0. And then all these terms are 0. So that it's as though it didn't help me. But if I factor out the x squared down there and cancel those, now all of these terms will go to 0, but I still have these constants that will stick around. So this is 1 over negative 1/2 or negative 2. Any questions about that guy? Okay. Anybody else have any questions? All right, well, if you guys don't have any other questions about these problems, as I said, that's all of the information for the next exam. We've already discussed that we're going to have the review on Monday and the test on Wednesday of next week, correct?